Good afternoon, everyone. I'm Yinxiao Feng, a fourth-year PhD student from Tsinghua University. It's my honor to be here to share our recent research about parallel simulation of chiplet-based large-scale networks. This is my outline today. Since traditional network researchers may not familiar with chiplet, I will firstly introduce some background about chiplet and chiplet-based network. First of all, let's look at recent trends. As we all know, the Moore's law drives the chip performance growth. However, in recent years, the workloads, especially AI, grew much faster than the Moore's law. As a result, there is a big gap between the workload and the chips. Therefore, we require more powerful scale-up and scale-out methods to meet the workload requirement. Generally speaking, the traditional scale-up method is to increase the scale of one node or one server, which focuses on the throughput. The scale-out method is to increase the number of servers, which focuses on the scalability. However, recent workloads, such as large language model training, require both the high throughput and the large scalability. So the large gap is calling for a more scalable scale-up method. That is the chiplet-based network. Let's see what is chiplet and why we use chiplet. That is mainly because Moore's law itself is hard to sustain nowadays. On the one hand, the device density approaches physical limits, and the technology development slows down. Look at the picture. We go from 5 nanometer in 2020 and 3 nanometer in 2022. 3 nanometer is still the most advanced technology in 2024. More advanced technologies such as 2 nanometer and 1 nanometer are becoming increasingly difficult to realize. On the other hand, the die size also reaches physical limits, which is the lithographic reticle size. Since both the density and the size of a single die are hard to increase, the only way to maintain Moore's law is to integrate more dies in a package. That is the chiplet architecture. As shown in the picture, advanced packaging and high-speed wireline technologies have made great progress in recent years. As a result, chiplets can be integrated in a single package with very high density. The internal bandwidth is extremely high, the package is extremely large, and the I/O port number is also very high. We can see that the chip architecture is very different from the past, thus creating challenges for network architectures. Let's see some examples. This is Intel's Sapphire Rapids chip, which consists of 4 dies. On each die, there is a 2D torus. On chip. There is a 2D torus on chip network. And on the package, 4 dies form a large 2D mesh network. On the 4 corners of the package, there are 4 UPI interfaces for higher level networks. This is a typical chiplet-based network. We have a network on chip, a network on package, and a network among packages. There are also many other examples. TensTorrent implements a folded 2D torus on chip and scale the chip into a larger 2D mesh. Since 2D mesh is not scalable enough, 2D mesh network on chip can also be scaled out into high radix networks. As shown in the right picture, 2D mesh on chip network is scaled up into hypercube topologies. Overall, in chiplet-based networks, network on chip is scaled up and scaled out into a larger system-level network. So what is the difference between traditional networks and chiplet-based networks? Traditionally, on-chip network and off-chip network are decoupled by switches, NICs, or I/O routers, so they can be designed and evaluated separately. As for network of chiplet, on-chip network and off-chip network are tightly coupled. The entire network must be designed and evaluated jointly rather than separately. It means that we may need to evaluate the entire fine-grained core-to-core network at a data center scale. That is challenging. Let's see another example. The chiplet-based network can be very large with some advanced packaging technologies, such as wafer-scale integration. As shown in the picture, the Tesla Dojo system contains up to 3,000 of D1 dies, and each die has 360 nodes, so the entire Tesla Dojo system has over 1 million on-chip nodes. These 1 million nodes are interconnected as a complete network. To design such a system, we need to consider the core-to-core topology, core-to-core routing, core-level scheduling, core-level fault tolerance, and fleet-level transmission. Everything is fine-grained, but the entire scale is extremely large. So the difference brings challenges for evaluation. Traditionally, the on-chip network usually has no more than hundreds of nodes, which can be easily evaluated even with cycle accuracy. Also, the off-chip network, which is the NIC-to-NIC network or switch-to-switch network, usually has no more than a few thousands of nodes. Since the network and the workloads are both distributed, we can also adopt a distributed parallel simulation. However, the chiplet-based large-scale networks are very different. They are core-to-core networks, thus there can be millions of nodes. At the same time, the simulation is very fine-grained, evaluating 1 second requiring simulating billions of cycles. Besides, these nodes are not distributed, but with a unified memory space. So it is also very hard to implement a distributed parallel simulation. Let's see what is the limitation of existing simulators. All the existing cycle-accurate simulators, including Buxim, Garnet, are single thread, so they are slow. Besides, we profiled the simulators. Most running time is consumed by unimportant circuit stages. For example, the round-robin allocation behavior is very time-consuming to simulate. There are also coarse-grained event-based simulators such as OMNET++, NS3, and SST. These simulators support distributed parallel simulation, but require manual partition and introduce extra programming overhead. Besides, the chiplet-based network is usually shared memory, so the distributed parallel simulation is not suitable. In conclusion, an ideal simulator for such a network is supposed to be cycle-accurate, very efficient, and not requiring extra programming. After introducing the background and the motivations, I'd like to show how we design a new network simulator. We adopt a new packet-centric architecture, combining the advantages of traditional cycle-based simulators and the discrete event simulators. In the network-centric architecture, all the key status values are stored in the network instance, which is not easy to parallelize because the chiplet-based networks is not easy to partition. In CNC, which is a packet-centric network, the key state values are stored in multiple packet instances. A packet queue is maintained based on the injection time, and all packets are updated every cycle sequentially. Such an architecture fits the first-come, first-served policy well and is easy to parallelize. Let me show some details. This is a packet vector, which contains all the packets in the network. Every cycle, new packets will be injected into the network. So the traffic manager will generate the packets and append them to the end of the vector container. It is clear that all the packets in the vector follow the injection order. And every cycle, all packets are computed and updated sequentially. The worker is responsible for all the computation. For example, if the packet just arrived one router, the worker will compute the routing and return candidate routes. If the packet requests for a link or a buffer, the worker tries to allocate the physical resource and return the result. In the single-thread simulation, the single worker will process each packet one by one. Packet 1, packet 2, and packet n. Since all the packets are in injection order, the processing is also in injection order. available resource will be directly allocated to the request regardless the following packets. So if a resource is requested by multiple packets, the first inject, first serve policy naturally achieved. As for releasing resources, if we let the worker immediately release resource, then a later packet in the queue may allocate again in the same cycle. This is not allowed. So we only mark the to-be-released resources in the first iteration, and then release them by another iteration separately. The second iteration is very quick because we do not apply any real computation but release resource or delete packets. After 2 traversals of the packet vector, we compute a network update of 1 cycle. We complete a network update of 1 cycle. So the key of the packet-centric architecture is that we leverage the order of packets in vector to implement an efficient first inject, first serve simulation policy. It is very simple, so it is very efficient. Besides, such a packet-centric architecture is also easy to parallelize. The traditional network parallelism, which partitions the entire network into several sub-networks, can be implemented. As shown in the figure, we can manage 1 separate packet vector per router. Since resource competition only happens within the same router, all these vectors can be processed in parallel. In this case, the allocation policy becomes the first come, first serve. First come means first reaching the router. Besides the traditional network parallelism, all the packets in the same vector can also be processed in parallel. We call this packet parallelism. In the multi-thread simulation, the packet queue is regarded as a workload pool shared by all worker threads. Each worker thread sequentially fetches 1 packet from the queue for processing. For example, packet 0 is dispatched to worker 0, and then packet 1 is dispatched to worker 1, packet 2 is dispatched to worker 2. When worker 0 finishes computing of packet 0, a new packet will be dispatched to worker 0. Also, packet I+1 is dispatched to worker 1 after finishing computing of packet 1. So all the packets in the vector is dispatched to any idle worker one by one until finishing all the computation. Besides, to prevent too frequent dispatch, we can also dispatch multiple packets to a worker at a time. We call this multi-issue. For example, we can dispatch packet 012 to worker 0 at a time, and dispatch packet 345 to worker 1. Each worker will process these packets sequentially. This is how we achieve packet parallelism. Very simple and so very efficient. Let's see more details about the implementation. Since synchronization seriously affects the performance of multi-thread, we adopt an atomic-based mechanism. Shared resources, including buffers, links, are set to atomic variables. The first packet of a thread that successfully modifies the atomic variable wins the competition of some resources. To maximize speed up, we let the thread contention decide the allocation of resources instead of any manual handling logic. This is the key of the efficient parallel simulation. Compared with the single-thread simulation, the multi-thread program no longer follows the strict first inject, first serve policy. Later injected packets may win the allocation in the competition with early injected packets. As shown in the figure, though packet 2 is dispatched to worker after packet 0, due to the randomness of thread execution, packet 2 may win the allocation before packet 0. We call this a multi-thread inconsistency. So is the multi-thread inconsistency fatal? Actually, inconsistency is only about the allocation result. But allocation policy is not what we are really interested in. Different policies, such as the round robin, first come, first serve, first inject, first serve, have the advantages and the disadvantages, but they do not seriously affect the overall performance. What we are really interested in is other key issues such as topologies, routing algorithms, collective communication algorithms. If we need to evaluate allocation policy itself, sorry, CNSIM is not applicable. Another question is that the variance of the single-thread and multi-thread execution. Actually, since all packets are dispatched to threads in injection order, early packets are still more likely to win the competition. We give the estimation of probability for inverted allocation. Put it simply, the probability of inverted allocation is very low. Experiments also confirm this. CNSIM also has many other features. Since time is limited, I will only give a brief introduction. Existing cycle-accurate network simulators are designed for on-chip networks, which usually have uniform link widths. However, for the chiplet-based networks, the link on the chip, the link on the package, and the link off the package have a big difference. So CNSIM support a heterogeneous router and link widths. We also catch the result of routing computation to speed up. And we also integrate CNSIM with real workload traces. Then I'd like to show some results. As shown in the left figure, the single-thread CNSIM is more than 10 times faster than any existing cycle-accurate network simulators for the small-scale networks. For the large-scale networks, CNSIM is originally 4 times faster than the booksim. After enabling hyperthreading, CNSIM can also be more than 10 times faster. As shown in the right figure, though we catch the partial routing result, the memory consumption is still very small. This is mainly because we do not record the request used for allocation computation. As shown in the left figure in this slide, multi-threading achieves significant speed up for large-scale networks. Nearly four thread can achieve nearly 3 times speed up. Compared with the single issue, the multi-issue scheme reduces the thread contention among multiple workers, thus achieving better speed up. The latency deviation of multi-thread inconsistency at most conditions is less than 0.2%. When the traffic is heavy, the inconsistency is slightly higher, but the deviation is still less than 0.5%. So multi-thread inconsistency is not a problem if we are not evaluating the allocation policy. The real reason why we design a new simulator is mainly because we have troubles in simulating large-scale chiplet networks. For example, we want to evaluate the performance of the chiplet-based switchless Dragonfly, which is motivated from Tesla Dojo. Though Tesla Dojo system is already large, we propose a more high-radix way to interconnect wafers, that is the Dragonfly topology. When we want to evaluate the performance, the routing algorithm, and the collective communication algorithms, we found that it is really time-consuming to simulate such large topology. So we decided to design a new simulator. Previously, we used booksim to evaluate the chiplet-based networks. The heterogeneous link-based networks are not too large, about tens of cores or a few hundreds of cores. However, the entire parsec traces include over 100 billion of cycles and 3 billion messages. One complete evaluation requires to run the traces for more than 10 times. So when we use booksim, we need 10 days to finish the entire evaluation. Now, by using CNSIM, 1 day is enough. Also, the entire chiplet-based switchless Dragonfly. Each latency curve requires running from 0.1 to 1 fleet per cycle per node injection rate. By using CNSIM, we only need a few hours to draw the curve. Personally, CNSIM has helped me a lot. I hope it will help more network architecture researchers. In summary, to address simulation challenges of chiplet-based large-scale networks, we designed a new cycle-accurate network simulator. We sacrifice the simulator's ability to simulate the allocation policy in exchange for simulation efficiency. We implemented the packet-centric architecture and the packet-parallel hyperthreading, improving simulation speed by an order of magnitude. Our simulator also has many other features and is open sourced to the community. Thank you.